Okay, welcome to lecture here. We are continuing on here with chapter 2, I think. We'll get started here in just a second, and see most of you are putting here in the chat box, so thank you very much for the roll there. Everybody in. Okay, so as you know, we are having a quiz today, and again, the plan is I'm going to lecture here for a little bit. We'll stop lecture early. You then could go onto Canvas and through Proctorial, like that Proctorial practice quiz, you could take the quiz, and then you could go off to either lab or discussion at 7. So we're going to do a little bit of lecturing here, and like I said, we'll stop early, and should give you plenty of time to kind of go do that. And then again, if you have lab today, obviously you need to go to lab. And if you have discussion, you'd come back with me at about 7 and for discussion. There is a time limit. It's about 25 minutes to quiz. So you got about 25 minutes to take the quiz, and which should be plenty of time, I believe. And again, we'll stop early enough for you to do that and everything. It is based on, I gave several quizzes this week, but I believe it's based on, for our class, it is chapter 1 is what it's on for our class. Basically the significant figures, conversions, density, temperature. I think that was all chapter 1 of. I will be posting Monday's lecture. It just, something happened with the recording, so I just got to fix it, and then I'll get it up there. Probably sometime today or tomorrow, the latest, it'll be up there, the recording. Okay. You do need a calculator. You might need something to write with to work out a couple of the problems. But yeah, you need a calculator, something, a scratch piece of paper, maybe to work out some problems. And you'll be given some conversions, and pretty much that's all you need. You don't need a periodic table on this one, so you won't be given a periodic table. Again, you need to take it using the Chrome, the webcam, and the Proctorial thing as well when you do it. Okay. And we'll talk a little bit about the quiz and sort of the process that you need to do when we stop. And we'll talk about it towards the end. But let's get going on some lecturing here, also because Monday's a holiday, I think, as well. So let's do that. Okay, so we were talking about electrons. And we're talking about basically where electrons are in the atom and sort of how they are. We're kind of getting into the process of sort of their order and everything in terms of their locations. And as we sort of finished up on, they pretty much could be in sort of two locations, or not two locations, but they could be in a few different locations. And these are what are referred to as orbitals. And they're sometimes referred to as atomic orbitals. And that is S, P, D, and F. And if you remember, when we talk about orbitals, these are really the theoretical places in an atom where an electron could be housed. And every individual orbital, no matter which one it is, so for example, represented by these little lines here, every individual orbital could only hold a maximum of 2 electrons. And when we talk about s orbitals, there's only one type of s orbital, which means you can max out an s orbital with 2 electrons. Now, that's different than p orbitals. There's actually 3 different types of p orbitals. And since there's 3 different types of p orbitals, each one could hold 2. So that is 6 electrons if you max them out. D orbitals, there's 5 different types. And each one could hold 2 electrons, which means you can max it out at 10 electrons. And f orbitals, there's 7 different types. And if you max them out, that'll be 14 electrons in that case. When we talk about sort of a couple of things here, this is like our n equals 1, n equals 2. That's the energy levels. 3, n equals 4. And these are sometimes referred to as, if you take the whole entire thing here, this is sometimes referred to as a level, or a shell is sometimes referred to. And for example, on the n equals 2 shell or level, that's kind of the second energy level. N equals 1 is the lowest in energy, closest to the nucleus. And as you go above n equals 2, n equals 3, n equals 4, and so forth, those are higher energy levels. And now individually, when we kind of look at, say, just the 3p orbitals, all of these 3p orbitals together, this is what is sometimes referred to as a sublevel or a subshell. Just like this here would be the 3d subshell. Over here, this would be the 4p subshell. And that's different again if I was talking about the n equals 4 or n equals 3 level or shell. That would be everybody that's contained in there as you go through here. So one way you could kind of quickly calculate the maximum number of electrons on a shell or level is to take 2 times n squared. N is that principal quantum number, which is the energy level. You square it and then times it by 2. So for example, if we did the n equals 2 level, 2 squared is 4. And 4 times 2 is 8. And what that means is if we filled up this entire level with electrons, we would max out at a grand total of 8 electrons. If we filled in the whole entire row there, would be 8 electrons. So it's really important to know that basically S's could hold 2, P subshells could hold 6 electrons total, D subshells could hold 10, and F subshells could hold 14 electrons. Now, if you know that, and we're going to talk about sort of the order that occurs, how these electrons go in. Electrons pretty much go in at lowest energy until that's filled, goes to the next energy level, and keeps going higher in energy until pretty much all the electrons have been distributed. Now, before I scribbled all over this, this is what all the energy levels look like in, say, hydrogen, where there's only 1 electron. And what you see in here, again, before I scribbled all over it, is everything with the 3, for example. That 3 represents the n equals 3. And that basically tells you it's on the 3rd energy level. And all the guys that have 3s are exactly equal in energy, just like all the ones that have 4s, which tells you it's on the 4th energy level. And 1 tells you it's on the 1st energy level. But all these guys with the 4s also are perfectly equal in terms of energy. What actually happens to those shells and subshells as we put more electrons in, more than 1 electron, is there's actually a switch that occurs. And again, just for reference sake, you can kind of see everything looks equal. When we get more electrons involved than 1, they're no longer equal. And what that affects is basically the order at which electrons would go in. Electrons would start here at the bottom, and they actually do go in opposite of each other. So if each of these arrows represents an electron, one goes upwards, one goes downward. The next one would go here. This is the next lowest in energy. The next one would go here to the P. Now, there's actually 3 different P orbitals in this subshell. And just for you know how it goes, they actually go in 1 at a time. So they would first go in 1 at a time, just like this, and then they would come back and pair up. And there's a rule that we really don't talk too much about in here, but there's a rule that basically tells you when there's more than 1 orbital, basically an electron will go in 1 at a time and then come back and sort of pair up. They would then go here. It would then go here again, 1 at a time, filling up and coming back and pairing off. And now here's really where the change sort of occurs. We're going to go from the 3p orbital. The next lowest in energy is actually the 4s, and that guy would get electrons. Then we go back to the 3d and start filling those guys up if necessary. So there's this sort of change that occurs once we get more electrons in. And there's a thing that you can make, looks like this kind of from your book, or you have a similar one. You could use this one, or you could do this. And I'll just show you, this is a really easy thing that you can kind of recreate. What we talked about is on the first energy level, there's S's. So you just go 1S, 2S, 3S, 4S, 5S, 6S, and 7S. Then you start with the P's on the second. So 2P, 3P, 4P, 5P, 6P, and 7P. Then the D's happen on the third energy level, 3D, 4D, 5D, 6D, and the F's don't start until the fourth energy level, 4F and 5F. So this is something you can kind of create really easily. And again, if you start here and go down 1S, 2P, 3D, 4F, that's where these orbitals first start. And we always start in terms of electron configuration, kind of following the arrows, and we zigzag back and forth. And this will give you the proper order of how electrons go in when we write something like electron configuration. So if you know this, which you should know, are how to create it, like we just did right there. And if you know that basically S, the maximum electrons is 2, P is 6, D subshell is 10, and 14 for our Fs, you should be able to write any electron configuration that you would need to do. So let us take a look at how to write electron configuration. Electron configuration is essentially the order at which the electrons are put into an atom. And there's a special way that we sort of write it, and we're going to talk about it here in just a second. But we're really interested in the electrons. So something that we talked about earlier was that the atomic number is the number of protons, which is our positive guy. And remember that if we are dealing with something that is neutral, it would also equal the number of electrons, which are negative. So if we use the atomic number for an element and it is neutral, the atomic number, which is our number of protons, will equal the number of electrons. So let us talk about how to write electron configuration. So we're going to start with the easy one here, which is hydrogen. And again, I'm just going to kind of recreate that thing. You may want to look at that thing that we were just looking at, just to kind of show you, how it goes. Let's recreate some of it here. All right. So again, we're always going to start here, no matter what you do. Whenever you're starting electron configuration, you always want to start there. So here we have a atomic number of 1, which means it has 1 proton and thus should also have 1 electron in this case. So the electron configuration for hydrogen would be 1s2. And what this means is this first number is that principal quantum number, which is, again, a fancy word for energy level. And again, it's really just the energy level. The S tells us what orbital our subshell it's in. So if you remember, we sort of talked about these guys as being like maybe rooms in a hotel, sort of where electrons could be. And the number on top, which should not be a 2, I'm going to erase that. I'm sorry about that. That should actually be a 1. Thank you. Got ahead of myself there. It should actually be 1 on top, which is because it only has 1 electron. So it should be 1s1, and that is how many electrons are in the orbital R subshell. So the electron configuration should be 1s1 for hydrogen. Then this is how you should write it. The 1 here is a big one, small s, and the 1 up here is a superscript. No commas, no weird thing people always like to do, dashes, I don't know, other things that people do. So that is how you should write it. Continuing on to number 2 on the periodic table, which has 2 protons, also would have 2 electrons. So again here, starting up on top, we would come down to here, and this would be 1s2 in this case. Again, energy level is the first number. the orbital that those electrons are in, and now the 2 electrons in that particular orbital, which would be 2. Now, because that is an s orbital, if you remember, the 1s pretty much is now filled. So any more electrons has to go to the next orbital that's available, the next lowest energy orbital. And that happens when we go to lithium. Lithium is 3, which means it has 3 electrons. And again, here, coming back to our thing, we would start here. It would be 1s2. And now that we filled that, we zigzag back around and we come to this guy, and it would be 2s1. And so this guy here, it would have a configuration of 1s2, 2s1. Yeah, so this is the orbital diagram, and we really don't do too much about orbital diagram in this particular class, but just to kind of show you, an orbital diagram is something that looks like this. So for this particular guy, I'll just draw it this way, not right in terms of energy, but I'll just do it this way. And how the electrons would go in, for example, is one arrow would always go up first, is how you do it for the first electron that goes in there. Second arrow goes down. And then when we would go to the next orbital, the next electron would be signaled upwards. So it's always up, down, unless you have a choice. And as we can see just from this, which again, this is what is sometimes referred to as the orbital diagram, which again, we won't do too much of in this class, but this is what is referred to as the orbital diagram. We can see that in the 2s orbital now, we do have space for one more electron to go in there. And that happens when we go to number 4 here, which is beryllium. That means it has 4 electrons. So again, going back here, we're going to start up on top again, always start here. So it's going to be 1s2. We again now will zigzag back here, and we will now be able to fill in this guy with the next electron. And we will have 1s2, 2s2 in this case. And again, just to kind of keep track of where our electrons are at this point. First one went in here, next one went in here, third one went here, and the fourth one went like this. This is what is sometimes referred to when you have 2 electrons in an orbital, as those electrons are what are referred to as being paired. Their spins are paired. They're basically heading in opposite directions. Is basically what that means. Now we can also see here from this sort of picture, and again, you don't have to worry too much about the picture here, but we can see we absolutely have no more room in this orbital for any more electrons, which means if we have more electrons, we need to go to the next lowest energy orbital or subshell to put those in. And that happens when we get to number 5. So number 5 would obviously be boron here. It has 5 electrons. And again here, starting up on top, going to our 1s, zigzagging back to our 2s2, and now the next lowest brings us to the 2p orbital in terms of where those electrons would go. And that means we would have 1s2, 2s2, 2p1. And if you're not sure how many electrons you're putting in, you pretty much can count the top numbers, 2, 4, and 5 electrons. And again, what this really means is, I'll draw a little bit better in terms of energy. On the first energy level, again, we put 1 electron in, 2 electron ins. The next electrons go into our second energy level with our 2s. And now the 5th electron will actually end right here. And again, each of these lines represents an individual orbital. Each one could hold 2 electrons. So if you're just doing the math here, you have 2, 4, and 1 more in the first one it could go. So this is, again, a subshell that could hold 6 total electrons. So we now have plenty of room to sort of fill in the rest of these. And let's continue on with that, which is number 6 is carbon. And that, again, means it has 6 electrons. So 1s2, 2s2, 2p2. And again, in terms of if you want to visually kind of see what's happening, again, this is our n equals 1 level, our lowest in energy, first electron, second electron, third electron, fourth electron, fifth electron. And now when we get actually a subshell where there's multiple orbitals, the way it goes in, and again, outside of our class in terms of why, but what happens is the actual electron goes to the orbital next to it. And it does fill up one at a time, like I mentioned earlier, and then comes back and pairs off. We can now see that we actually have 2, 3, 4 more spaces for electrons in this subshell. So we might as well finish this guy out here, going to number 7, which is nitrogen. 7 protons also will have 7 electrons, which means it should be 1s2, 2s2, 2p3. Again, if you count up the top, 2, 4, and 3 is 7. Again, kind of filling in as we're going through this. So you can kind of visually see what's happening. Again, first one goes there, next one goes there, third one goes into there, fourth one goes into there, fifth goes there, sixth goes there, and again, the seventh one actually will go here at this point. At this point, we have room in each of these orbitals for one more electron each, and they will now have no choice but to come back and start going the other way and pairing off at this point. There's a rule that basically says it's really more stable when all the electrons are going kind of in the same direction. And that's what's sometimes referred to as parallel spin. So continuing on, Z is the atomic number. So that's the number that we find on the periodic table. And again, that is the number of protons. And because we're assuming that these guys are neutral, that is also the number of electrons, right? So if something's neutral, it's got to have the same number of protons and the same number of electrons. The 2p sublevel can hold a total of 6 electrons. So right, this is our 2p sublevel or subshell. And at this point, it now has 3 electrons. So the next ones are going to come back in and fill this up until it maxes out at 6. So why don't we continue on with that path there. Number 8, which is oxygen. Again, number of protons is 8, which means it does have 8 electrons. So it should be 1s2, 2s2, 2p4 in this case. And again, just visually what's going on at this part. So n equals 1, n equals 2, 1, 2, 3, 4, 5, 6, 7, and now the 8th one will actually come back and go here. That will now fill up this orbital. This orbital, individual orbital, is now full because it has 2 electrons. I am clearly not drawing this properly in terms of energy, but you get the idea. Lowest, lowest, next lowest. We have room, as you can see here, for 2 more electrons until that subshell is filled. So might as well finish it out since we're close to the first 10. Number 9 is fluorine, which means it will have 9 electrons as well. So again, 1s2, 2s2, and 2p5. And again, I'm still following that zigzag little chart that we had a few slides back. And I'm still stuck on the 2p because I have not completely filled it. And we don't move on until we've completely filled the subshell. We don't move on to the next one. And again here, we look at it. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have now filled this guy and filled this guy. We can see we have room for 1 more electron there. And that will happen at number 10, which is neon. And neon's number 10, which means it has 10 protons and should also have 10 electrons. So we might as well fill that guy out. So 10 electrons. And again, 1s2, 2s2, 2p6 at this point. And filling in filled 4, 5, 6, 7, 8, 9, and 10 electrons. You can now see that all these individual orbitals are filled. We have now filled our 2p subshell. And at this point, if we needed more electrons, we would have to go to the next guy in line. And again, I'll just kind of make this part of it real quick. 2p, 3p, 4p. So far we've zigzagged this way. We zigzagged this way. We have come through this guy. If we had more electrons at this point, we would continue now to the 3s and work our way through it. You can write electron configurations for cations and anions as well, things with charges. And we'll talk about that when we're kind of towards the end here, electron configuration, what happens in terms of when things do get charges. But you can write definitely electron configuration for things with charges. Any questions on how to write electron configuration? You should write electron configuration like this. I don't know about the newest version of the lab manual, but the old lab manual, she used to write it kind of weird. She used to just use numbers like 2, 8, and so forth in terms of electron configuration. Don't do that. Write it like this. So if she still does that in the lab manual, the only place I've ever seen a person do that is in that lab manual. Kind of writes the electron configuration kind of weirdly, just uses numbers and stuff like that. You should definitely write it like this. Any questions on that? So why don't you try this one? Why don't you try argon, which is 18 electrons? Why don't you write the electron configuration for argon, which has 18 electrons? Okay, so let's take a look. I see some popping in there, so I think we're looking good. So we got 18 for the atomic number, which means, again, it would have 18 electrons. Again, when you do this, as you just saw me do on the paper here, this, again, is something that you could recreate yourself very quickly. And again, we always start up here. So coming this way, we would need 1s2. Zigzagging back this way would give us 2s2. Coming this way, we will take 2p6. Again, if you count the top, we have 2, 4, and 6, which is 10 electrons. So we still have 18 more to go. So we will continue past here. We will now come to the 3s, which could hold a maximum of 2 electrons. So we're now up to 12. We still are not there, so we need to zigzag back this way to our 3p and 3p6 because it could hold 6. And if we count the top there, 2, 4, 6 is 10. plus 2 more is 12, and 6 more is 18. So this would be the electron configuration for argon. Question on that? Looks like everybody's getting it in there in the chat box, so that's good. Any questions on how to do that? Again, no commas, no dashes, no weird things. You know, don't just kind of write it like that, like you see it on the screen, and that should be the correct way. Now, when we look at the periodic table, there actually is blocks on the periodic table. And when you look at the first two groups, that is the S block. And if you remember, S could hold 2 electrons. And if you look here, this is S1 and S2. Over here, groups 3 through 8 is the P block. And if you remember, P subshell could hold a maximum of 6 electrons. So if you look at, say, the top box here, P1, P2, P3, P4, P5, and P6. The transition metals in here, is the D block, and it could hold 10. So first box is D1, D2, all the way to D10. And those two guys on the bottom is the F block, which could hold 14. Again, if you count all the boxes on the bottom of the periodic table, it actually is 14. You could actually use the periods. This goes like 1, 2, 3, 4, very badly drawn, 5, 6, and 7. And as you go this way, and you can literally count off the electron configuration by doing that. So for example, if we wanted, say, lithium, which is right about here, we would start here. This is hydrogen. Hydrogen would be 1s1 to helium, which is here, would be 1s2. Coming down here to lithium would be 1s2, 2s1. You could actually count it off all the way across. Over here, this would be oxygen that we did somewhere in this ballpark. This would be 2p1, 2p2, 2p3, and 2p4. You could actually count it off using the period number and also the block. There are some exceptions, though. This is the 4th period here, about here. And this is SC. And this is 4s1, 4s2. But remember that the d orbitals don't begin until the 3rd energy level. So this row right here is actually 3d, and then 4d, 5d, 6d, and so forth coming down. And remember that F's actually start at 4f. So the D's are 1 behind the period number. And the F's are actually 2 behind the period number. I personally would probably not count it off the periodic table unless you really know what you're doing. I would probably use the zigzag thing, and you'd probably be in pretty good shape because if you really are not sure, you will get into some trouble. Now, when we look at something like potassium, for example, which is 19, again, it would be 1s2, 2s2, 2p6, that is 10, 3s2, 3p6, which is 18, and potassium is 19, so then we would go to 4s1. So again, if where's that little thing I was zigzagging? So 1s2, 2s2, 2p6, 3s2, 3p, and then we go to our 4s next. And as I see in here, when we look at this part of the configuration, and we count up how many electrons there are, that is 2, 4, 10, 12, 6 is 18 electrons. If you look on the periodic table for number 18, it is our good friend argon. And you can write electron configuration by putting argon in brackets and then continuing on with the configuration. This stands for the electron configuration for argon. And this way of writing it, which I saw somebody write it, I think in the notes there or the chat with the neon, this way of writing it is what is sometimes referred to as the noble gas configuration. And because it's a noble gas configuration, you do need to know the order, yes. So you do need to know that's the exact thing. And again, it's something that you could kind of recreate pretty quickly on a paper and stuff like that. So you do need to know how to memorize it or how to recreate it pretty quickly. This is what is sometimes referred to as the noble gas configuration, which means what goes in the brackets needs to be a noble gas. Noble gas is group number 8 on the periodic table. So for example, if we look at sodium, which is 11, and we write its electron configuration, 1s2, 2s2, 2p6, 3s1. If we take this part of the configuration through here, that is 10 electrons. Again, if you go to the periodic table and look at number 10 is neon. So the way we could write this is neon in brackets and continue on with 3s1. So again, that would be the noble gas configuration. So it is always the noble gas that comes right before whatever you're trying to write in terms of its electron configuration. Questions on that or writing noble gas configuration? Okay. Now, somebody asked about things with charges. So when we look at the periodic table, I probably shouldn't write right there, I don't think. Let me try to find a spot. Actually, here's, let me do this. Here we go. So when you look at a periodic table, remember this is group 1, this is group 2, group 3, group 4, group 5, 6, 7, and 8. And when things gain charges, there are certain things on the periodic table that will always make a fixed charge no matter what the situation is. Everybody in group 1, no matter what the situation is, will always make a +1 charge when it does make a charge. Everybody in group 2 will make a +2 charge. Everybody in group 3, which is pretty much aluminum, will make a +3 charge. When you go to group 5, they actually will become negative. These are the nonmetals, so -3, -2 in group 6, and -1. Remember, you got that staircase kind of coming down here, and above the right of it is nonmetals. And the transition metals can have multiple types of charges, except for a kind of a 3-pack here, zinc and cadmium. There will always be +2. And if you hang a left there, silver will always be +1, no matter what the situation is. So when things gain charges, as we talked about when we talked about electrons, protons, and neutrons, it is just the electrons that are affected. And you do have to take that into account if you're writing an electron configuration. So for example, if you take something like oxygen with a -2 charge, the minus means that it gained electrons, and the 2 means that it gained 2 electrons. So oxygen's atomic number is 8, which means it also gained 2 electrons to become -2. It has 10 electrons, which means if we wrote the electron configuration for oxygen with a -2 charge, it would be 1s2, 2s2, 2p6 would be its electron configuration. Now, if something gains a positive charge, let's take our friend sodium there. Sodium, which is group number 1 on the periodic table, will make a +1 charge. Sodium normally has 11 electrons. The positive means it lost electrons, and +1 means it lost 1 electron, which means this guy would also have 10 electrons. And its configuration would be 1s2, 2s2, 2p6. And you may recognize, as we were just talking about, this has 10 electrons, the oxygen with -2. Sodium with +1 has 10 electrons. And the guy on the periodic table that has 10 electrons is neon, right? So oxygen with a -2 charge has the same configuration as neon. Sodium with a +1 charge also has the same configuration as neon. Things that have the same electron configuration, these are what are referred to as being isoelectronic with each other. Isoelectronic means they have the same electron configuration. And if you look at the periodic table, sodium is here, oxygen is like here, and neon is here. And what happens is, as we'll talk about in bonding in the next chapter, metals tend to lose electrons to end up just like the noble gas that came right before them. So when sodium loses its electron, it's able to back up and become just like neon in terms of electrons. While oxygen, when it gains 2 electrons, able to move 2 places forward and also end up with the same electron configuration as neon. The whole purpose of bonding is to end up with the exact same electron configuration as a noble gas. Noble gases are extremely stable, and that's why that happens, basically. Any questions on that? Okay, we're going to lay it up here so you have plenty of time to take your quiz and all that good stuff. So a couple things before you sign off here for lecture. Monday is a holiday, I believe. So we'll be back on Wednesday for lecture with everybody. So have a good week if you're out for the week. A couple things about the quiz. You do need, again, the computer, the webcam, the proctoral, just like that proctoral practice quiz. It should not ask you for a code. That means you are not using the Chrome browser with the proctoral installed. You will be given on the quiz some conversions to use. Is perfectly fine. You can use a calculator, perfectly fine. You could use a scrap piece of paper to work out things. You should not have notes out, yes? So I should not see notes or anything like that. It is closed book, closed notes, and all that kind of stuff. It will be okay. It's not an issue. I'm going to assume that you are looking down to work out things on your calculator and stuff like that. If you can arrange the camera view to get a little bit of a shot of you and your work area, that would be best, yes, if you can do that. So the goal here is, try to do the right thing. A reminder that there are different versions, so don't have the right answers on the wrong version or anything like that. You do not have any work that you need to upload here. It's just kind of all or nothing. Yeah. So you pick the right answer, enter the right answer for this quiz. On exams, you'll be able to upload work. But for this one, you don't have to upload any work or anything like that. There is an entire module that you need to go through. So you will be first asked to look at, there's an academic honesty agreement to look at. There's an electronic version of that where you could sign it electronically, just put your name in and your initials. Then that will open up the quiz for you to take, and then you can take the quiz and submit it. Again, you'll be able to see all the questions at once. There's one submit button at the end. Do not hit the submit button until you're completely done with the quiz. Otherwise, it will submit it, and you will not be reopened for you. It will also pop up there and go, are you sure you want to submit this? You didn't answer anything. So hopefully that warning will stop you as well. There is discussion after this. There is lab after this as well if you have lab today. So we'll do some discussion and stuff like that. I don't remember. I think there's maybe 7-ish or so or 8 questions, I think, on it. And again, you could work it on scratch paper, you and sort of your work area in the view. Any questions on any of that? So let me let you go so you can go do that. It is not up there right now. Give me about a minute or so. And there will be an announcement that will come out through Canvas with a link to it, but just in case, you could find it in the module section. Just give me about a minute or so here right now, and I'll go do that for you. Otherwise, have a good